Okay, shall we start? The recording team, can they hear? Can they hear? Mic is okay. Okay, good morning. So, yesterday we learnt about two different types of read heads, AMR head and GMR heads. We saw how it works, but we did not discuss the theory of them. Okay, few years ago I also did not know the theory very much in detail, but recently there is a book which you can read to understand the theory better. So, I am also quite new to this theory. So, today I may not explain all the concepts very well, but I will try my best. Okay. So, this one I am just teaching recently, only recently. Okay, so, let us go into the theory of magnetoresistance. So, before that we do a recap. So, we learnt about anisotropic magnetoresistance. So, in the case of anisotropic magnetoresistance, you have a device which looks something like this. So, you send a current through this device, and in the absence of any magnetic field, the magnetization of this device is at 45 degree, and if there is a magnetic field that comes from the recording media that goes in the upward direction, that field forces the magnetization to go this way. So, when the magnetization and current are perpendicular, we have low resistance state. Okay. Now, there is no magnetic field, it will come back here, and if there is a magnetic field in the down direction, it will force this magnetization to rotate towards this direction. So, now the magnetization and the current are parallel, you will have the high resistance. So, what the magnetic field from the recording media does is to make the magnetization go this way or this way. So, magnetization keeps fluctuating between this angle. So, you get high and low resistance depending on the magnetic field sensed by this anisotropic magnetoresistance sensor. Okay. So, this first concept we learnt. The second concept we learnt is about GMR, giant magnetoresistance. Okay. In the case of anisotropic magnetoresistance, you have only one ferromagnetic layer. You do not need two or three layers, you just need one ferromagnetic layer, and you may have some additional layers for additional complexity, but they are not that important in the functional understanding. If you look at this picture, we are just talking about one ferromagnetic layer and the magnetization being rotated. Okay. Magnetization gets rotated and it makes some angle with respect to the current, and that is what determines the resistance. Okay. Only one ferromagnetic layer. So, when it comes to giant magnetoresistance, for example, we have at least two ferromagnetic layers separated by a spacer layer. So, in the simple version of GMR proposed by Peter Grunberg, we have only iron, chromium, iron, only 3 layers, but in the study done by Albert Furt's group, we have 30 to 60 bilayers of iron, chromium. Okay. So, in this particular set of system, what happens is when there is no magnetic field, the two layers have antiparallel magnetization. So, in the absence of any magnetic field, you have two layers with antiparallel magnetization, with which gives rise to the highest magnetoresistance state. However, when you apply a very strong magnetic field along one particular direction, you force both layers to point in one particular direction, and that is where you see the lowest resistance state. Okay. So, parallel magnetization means low resistance, anti-parallel magnetization means high resistance. Okay. So, this is the phenomenon that they observed in 1989 to be precise, 88, 89 somewhere there. And we will be learning about TMR later. Okay. So, now let us move on to learn about the theory of GMR. Okay. So, to understand the theory of GMR, so you need to have some understanding of the energy bands. Okay. So, when we learnt about magnetism, I started with atomic magnetic moments. So, isolated iron atom had 4 Bohr magneton and things like that. Okay. But when you put atoms in a solid, say a piece of iron, then we know that there is a band structure evolving, and then that band structure determines the magnetic moment per atom, the electrical resistance and so on. Okay. So, here we have the band structure of nickel. Okay. So, if you see, on one side we have energy, and the other side we have density of states. Okay. So, on the x axis you have y axis you have energy, and x axis you have the density of states. Okay. So, if you look at this picture, the spin up electrons occupy this band and spin down electrons occupy this band. Okay. So, whenever a band below the Fermi layer is completely filled, then that particular ferromagnetic material is called a strong ferromagnetic material. Okay. So, in the case of nickel, this band below Fermi level is completely filled. So, they have this name. Anyway, that is not very important. Okay. So, in ferromagnetic materials, you will notice that the band where the up electrons get filled and the band where the down electrons get filled, they are shifted. Okay. There is a splitting of the band. So, in non-magnetic material they will be like symmetric, okay. But in ferromagnetic materials there will be a shift caused by the Heisenberg exchange interaction. Okay. So, this is what we call band splitting. So, the up spin electrons and down spin electrons, they have different density of states. Okay. So, that is something that you should know, because we will be using these concepts in the next few slides. Okay. So, to understand the magnetoresistance and the GMR phenomena that we are going to learn, we need to understand this two current model proposed by Mott in 1930s. Okay. So, in 1930s Mott proposed that the conduction takes place in two channels. Okay. So, he says that there is one channel for spin up electrons and one channel for spin down electrons. Okay. You can imagine it is like a two road. So, anyway, so a few days ago I also was saying these words, but I did not tell you the definition. So, when we say spin up or majority electrons, what do we mean is that the magnetic moment of the electrons is parallel to the magnetization of the material. So, for example, you have a layer with a magnetization along this direction, and let us say you send current into this layer. Okay. So, you have spin up electron, spin down electron. So, here I am naturally saying spin up, spin down, because I already have in mind that this is parallel to this. Okay. The magnetic moment of this particular electron is parallel to this. So, we call it spin up electron, and the magnetic moment of this electron is anti-parallel to this. So, we call it spin down or minority electron. Okay. So, it depends on the magnetization of the layer into which they are going. Okay. So, let us say you have magnetization of this layer down like this, and if you send electrons. So, in this case this will be minority electron. Okay. This is minority electron, this is majority electron. Okay. So, it is with respect to the direction of magnetization, whether it is parallel or anti-parallel, then we have this definition. Okay. So, from this slide you just take that there are two paths for the two electrons. Okay. Spin up electrons go in one path, spin down electrons go in another path. Okay. So, we also learnt that the electrons do not go like straight, right, they undergo scattering. Okay. So, typically they get scattered from other electrons or phonons. So, they cover roughly around, I mean the mean free path is around 10 nanometer. So, they can travel around 10 nanometer. Okay. So, this 10 nanometer is very critical because only at this scale we will see effects like GMR. Okay. So, when you make a GMR sensor, for example, you may have one layer of a ferromagnetic material with a 3 nanometer spacer, say 2 nanometer, another ferromagnetic material of 3 nanometer, something like that. So, the electron, if you send current this way, electron is not going to flow through only one ferromagnetic layer. Okay. It will go through all the layers. Okay. So, that is where this mean free path of 10 nanometer comes into picture. Okay. So, what is new in this slide is that because of the two current model that we just introduced, now we are looking at two electrons. Okay. Spin up electrons go in one path, okay. Spin down electrons go in another channel. Okay. So, that is the first point of the Mott's two current model. Okay. The second point of Mott's two current model is that Mott assumed that 4 s electrons are mainly responsible for the current. Okay. So, you know that in ferromagnetic materials we have 3D shells completely filled 4 s. So, you know that s electrons are the conduction electrons, right. So, they are responsible for conduction, d electrons are localized, and the scattering of these 4 electrons, 4 s electrons into d states is responsible for the resistance in transition metals. So, when we say transition metals, in this case you can say that iron, cobalt, nickel, they are all transition metals. So, right now we are focusing on these transition metals. Okay. So, you have atoms of iron, for example. So, we have nucleus of iron, nucleus of iron, nucleus of iron, and so on. The s electrons are moving from one side to the other side. These s electrons may get scattered into the d state. Okay. So, that is what gives rise to the resistance. You know the current is dq over dt, right. So, if lot of charges flow in a particular direction, we have a large current, but if charges get scattered into some localized state, then they are not flowing, right. So, that is why we have a lower current. So, if you apply a voltage, the current will be lower when okay, let us ignore this one. Anyway, let us not go into that detail. So, the scattering of s electrons into d state is responsible for the resistance behavior. Okay. So, it is given by this Hamiltonian, the scattering probability of some electron getting scattered from S into D state, and this is highest for the spin down electrons. Okay. So, to understand this one, you can look at this picture, you can see that there are more slots for S electrons to get into. Okay. That is one way you can understand. Otherwise, let us go back to the simple picture. So, in a simple scenario, I told you that ion atom has 5 up spin and 1 down spin, right. This is isolated ion atom, but in a real crystal we learnt that the atomic moment of ion is 2.2 Bohr magneton per atom. Okay. So, I did some simple calculation how we can arrive at this 2.2 Bohr magneton per atom. So, we can imagine that there are 100 ion atoms, sorry, in this case yeah. So, if you take 100 ion atoms, I am trying to simplify this picture. So, if out of this 100 ion atoms, let us say there are 10 ion atoms where you have this 5 up and 1 down spin. Okay. Then there are 90 other ion atoms where you have 4 up spin and 2 down spin. Okay. So, if you have 100 atoms, 10 of them have this configuration, 90 of them have 4 up, 2 down. Okay. Then this will give rise to 2.2 Bohr magneton per atom. Okay. So, in this very simplistic picture, you can notice that these 10 atoms will not accept any spin up electrons, because all the 5 states for the spin up is completely filled. Okay. They will not accept any spin up electrons, and these atoms can accept 4 spin down electrons. Okay. So, remaining 90, right. So, this 90 can accept 1 spin up electron or maybe 3 spin down electron. So, if you look at all these atoms, you can notice that all of them can accept more spin down electron. Okay. So, that is what this picture conveys. That is one thing. Secondly, there is, if you have a spin up electron, it does not go into a spin down state. Okay. The spin does not flip. Okay. So, S electron can only go into S up or S down. So, similarly, S down electron can go only into S down or D down. Okay. Okay. So, let us summarize what we have learned so far. First point is that there are 2 channels for spin up electron and spin down electrons. Second point is that S electrons are responsible for conduction and they can get into D state, and that is the one that gives rise to resistance phenomena, and this scattering potential is more for spin down electrons. Okay. Spin down electron gets scattered more. Okay. So, these 3 are the important points. You can also say another point is that the spin flip does not happen. Okay. Spin up electron goes as spin up electron, it does not flip into spin down electron. Okay. So, you can say these 4 points are the most important points of the Mott's 2 current model. Okay. So, with this, let us go to the next slide. Okay. So, this point I just said in the earlier slide. So, the spin direction does not change, and we just learned that 3D is almost filled, spin up 3D spin up is almost filled. So, nothing can get, I mean there is a very few probability that spin up electron will get scattered, mostly spin down electrons get scattered. Okay. So, we can draw a equivalent resistance diagram. Okay. So, now we know that this channel is for spin up electrons, we have another channel for spin down electrons. So, spin up electrons have two probability, S up can get scattered into S up, or S up can get scattered into D up state. The other one is S down gets scattered into S down gets scattered into D down. Okay. But we just notice, I mean we just discussed that D up is completely filled or mostly filled. So, the probability of S up electron getting scattered into D up is almost 0. Okay. So, we can remove this resistance. Okay. And this resistance is much lower in value compared to the S down electron getting scattered into these states. Okay. There are a lot of empty states. So, S down electrons can get scattered into these empty states. So, that probability is high. So, there is a high resistance for this. Okay. So, because of all this discussion, we can come up with a simple diagram. So, now the resistance for spin up electrons and spin down electron can be shown something like this. So, I told you this is 0 and this resistance is very small. So, for spin up electrons the resistance is small. You can, I mean in the discussion later I may use resistance or resistivity. Okay. Both mean almost same thing except the area, length and things like that. Okay. So, this resistance is much larger. So, you can see that the spin up electrons have a smaller resistance and spin down electrons have a larger resistance. Okay. Spin down electron gets scattered more. Question?
Resistivity comes from the density of states.
Yeah. Electron getting scattered into these empty states, and that is what gives rise to the resistance.
So, but sir, in the down spin there is some vacancy in the density of state. There are some vacant states. So, electrons can fill those states.
Electrons can go into these states. Yes.
So, like why the scattering happening here?
I mean these are the available states. So, the electrons can go there.
If I am passing a current through this, then majority will be down and the minority will be up.
No, majority means let us say you have a layer with a magnetization like this, majority is this.
But for upspin there is no density of states available.
Yeah, upspin does not get scattered much. I mean upspin, okay. So, that is why I had some analogy here which I did not discuss before. Let us say you go into a shopping mall. If there are 10 chairs, all chairs are filled, then you cannot sit, right. So, you will keep moving. Okay. On the other hand, if you find that many chairs are vacant, probably you will sit down, take rest, right. So, similar sense. So, if electrons find some states available, they may get scattered into, but if there are no states available, they will keep moving. So, resistance is high when the electrons do not flow, right. Yeah.
So, if I have a material with such like band states, like some density of state, and if I pass a charge current through it, then there is a probability that one kind of spins will get scattered and one kind will pass through it. So, in this case, like which will be passing and which will be scattering?
Yeah. So, which will be passing, which will be scattered, you can look at these empty states. Okay. So, for spin up electrons, there are like few chairs in the shopping mall. So, they cannot sit, they have no chairs to sit, they will move. Okay. So, spin up electrons will move. Okay. Spin down electrons, they have lot of empty states. So, they will get scattered into these empty states. So, spin down electrons will have more resistance. Yeah.
So overall, this material has a magnetization of upspin.
Upspin.
Because there are majority of upspin.
Yeah. So, we are looking at magnetization in this direction, and electrons of these two types are going into this material. Okay. So, when we say majority minority, we are talking with respect to the magnetization. Okay. So, for this particular magnetization, this type of electrons will go without getting scattered. The one with opposite magnetic moment compared to the magnetization, they will get scattered.
Like we can conclude saying that if the kind of spin state, the density of state is completely filled, the magnetization of the material will be in that direction.
Yeah, yeah, yeah.
That we can conclude.
Yes. So, it is like here this is completely filled. So, we can say the magnetization is in this direction.
We have few online questions.
Scattering of s electrons into d states. So, that is what I mean. So, s electrons instead of flowing through the conductor, they get scattered into the d states. D states are localized, that means they get stuck to the atoms, we can say. Spin down electrons are minimum because in any electronic configuration, excess electrons first spin up. Okay, I am not saying spin down electrons are in majority. So, I mean when we are talking about electrical resistance, the first point we said is that s electrons are responsible for conduction. Okay. So, the 4s electrons are responsible for conduction. Okay. So, these s electrons are the conduction electrons, they can get scattered into d states, that is what we are talking about.
This kind of like a different density of state for up and down spin generally forms in the material because of the hybridization of d orbital with some other orbital.
I mean this is from the Heisenberg exchange interaction. So, if you take iron, cobalt, nickel, so we can say that the Heisenberg exchange interaction causes this spin splitting.
So, this is a like conduction band splitting.
This is no, this d electrons are not conducting conduction band, right. Conduction band is this one, these two, these are the 4s. So, conduction band is not spin split. So, 4s and 4s up and 4 down are same. So, there is no spin splitting of 4s. So, you see this is s up, s down, and these states are equally filled. Spin splitting is happening only in the 3D orbital. Yes. So, this is what I was saying. So, the spin up electron does not get scattered much. So, it has a small resistance. The spin down electron gets scattered more. So, it has a large resistance. Okay, so, when I talked about spintronics, first I used this term without defining what it is. So, spin dependent scattering is also called asymmetric electron scattering. So, this happens due to the band splitting. So, we just learned that the spin up electrons get scattered less. So, they have a low resistance path. Spin down electron gets scattered more. So, they have a high resistance path. And this is coming because lots of empty states for down, very few empty states, few available states for the s down electrons to get scattered. Okay. And yeah, as I mentioned, I may use rho or resistance, and they are almost similar in concept except for this area and length. Okay, so people define this term called asymmetric scattering parameter. Okay, so rho r is the resistivity of spin down electrons. Okay. Rho up is the resistivity of spin up electrons. Okay, so now tell me this alpha is more than 1 or less than 1 for ferromagnetic material. For ferromagnetic material, is the alpha more than 1 or alpha less than 1? Pardon? More than 1. Okay. Because in ferromagnetic material we learnt that this is low, this is high. Okay, so we have high numerator and lower denominator. So, for ferromagnetic material alpha will be more than 1. Then for some other material you will have alpha less than 1, okay. Depending on the band structure, some material will have alpha lower than 1, some material will have alpha more than 1. So, if you look at the ferromagnetic material like iron, cobalt, okay, this is the two we can see here in this picture. So, the circle represents the resistance of spin up electrons. So, you notice that the spin up electrons have low resistance like what we have already discussed. Then the square represents the resistivity of spin down electrons. So, you can notice that they have a larger value compared to the other resistance. So, the alpha of ferromagnetic material is more than 1. So, in the case of cobalt, this is around 20. Okay, so, if you divide this value by this, you will get around 20. So, if you take chromium for example, here the other way alpha is less than 1, 0.3. Okay, this is a European notation, they use comma for full stop. So, this is 0.3 for chromium. Okay, I think that is all we need to take from this slide. We do not need to worry about beta here. Okay, so, we have two paths for spin up, spin down. The total resistance of this path will be like two parallel resistances. Okay, so, now let us go into some study carried out by the group of Professor Fert, who got the Nobel Prize of GMR. Okay, so, Professor Fert's group studied the spin dependent scattering in two systems. Okay. So, there is one system which they call type 1. So, type 1 is an alloy of nickel. So, for example, it can be like nickel cobalt for example to start with, and they will slowly remove the cobalt concentration . Something like this. Okay. So, they start with a nickel alloy cobalt, then slowly they remove every cobalt atom with ruthenium atom. Eventually, they will go to nickel rhodium. This is rhodium, right? Yeah. Nickel rhodium 50. So, they are changing the composition of cobalt and slowly moving to nickel rhodium 50. So, in this graph, if you look at this one, so here is nickel 50, cobalt 50. When you go this side, it is nickel 50, rhodium 50, and in between you have like a mixture of both cobalt and rhodium. Okay. So, that is the x axis of this picture, and in the y axis you have the resistance of this material. Okay, so, nickel is ferromagnet. So, we know that nickel has alpha larger than 1. Cobalt is ferromagnetic material with alpha greater than 1. Okay. But in this case, they are replacing cobalt with rhodium. So, rhodium has alpha less than 1. Okay. And we just learned that in ferromagnetic material where alpha is greater than 1, spin down electrons will be scattered more. Okay. Alpha is less than 1 means spin up electrons will be scattered more. Okay. So, let us go back to the definition. Alpha is the ratio of these two. Alpha is less than 1 means this will be more, right. When the denominator is more than the numerator, alpha will be lower than 1. So, alpha is less than 1 means spin up electrons get scattered more. Okay. So, what they do is they take nickel and in the here they have nickel and cobalt both scatter spin down electrons only. Okay. So, they have a color code. So, you can notice that this color, this dark green color represents the scattering from cobalt. Okay, the dark green color represents the scattering from cobalt, and the light green color represents the scattering from rhodium. Okay. So, cobalt scatters spin down electron. Okay. So, because of that you will see like a dark, lot of. So, this basically mentions that the spin down electrons which are going in this channel. Okay. So, this is spin up channel, top one is spin up channel, bottom one is spin down channel. So, in the spin down channel, cobalt scatters the spin down electron. Okay. This we already established, and the spin up electrons, they are scattered by rhodium. So, as you keep adding rhodium, so somewhere here, let us say now you have both cobalt and rhodium. So, rhodium scatters spin up electron, and because of that you will see the scattering of electrons by rhodium. Okay. So, in the spin up channel, electrons get scattered by rhodium. Okay. So, what it means is that when you have like say nickel 50, cobalt 25, rhodium 25. So, when you have this kind of system, cobalt scatters spin up electron, rhodium scatters spin down electron. Both the elements you add scatter two types of electron. As a result, when you have intermediate composition, your resistance is much larger. Okay. So, if you do not consider spin dependent scattering, the resistance may change like this, but because of the spin dependent scattering, like both the elements you add are scattering. So, you see a larger value than what is expected. Okay. So, in this channel rhodium scatters spin up electron, in this channel cobalt scatters spin down electron. Okay. So, this system is called type 1. Okay, let us keep this in mind, because this concept will be used for explaining the GMR. Okay. I am not very sure, sir, how do we understand this as a technical jargon? Electrons occupying the d states refer to their scattering into d states, the picture. I somewhat not very clear. If you can, please elaborate. Okay. I mean, in a simplistic picture, the flow of if electrons flow without get scattering, then resistance is low. Okay. So, electrons keep moving without getting scattered into some non-moving states, then we can say the resistance is low. Okay. So, to introduce this, I introduce the analogy of a shopping mall with empty chairs. Okay. So, let us say you are going around in the shopping mall. If you find some empty chairs, probably you will sit in the empty chair, take rest for some time, then again move. Okay. So, in that case your flow is affected. On the other hand, if there are no empty chairs, you will not sit down, you will keep moving. Okay. In that case your flow is not affected. Okay. So, empty states means electrons have a probability of getting scattered into the empty localized state, they will not move. So, they will have high resistance. So, d states are localized, right. So, if electrons get scattered into d states, they are not moving. So, they have a high resistance state, that is what I mean. Okay, now, let us come to another system called type 2. So, in the type 2 again it is like nickel. So, here is a nickel cobalt, here is a nickel gold, somewhere here is nickel 50, gold 50, cobalt 50, something like that. So, in this case both cobalt and gold have alpha larger than 1, which means both of them will only scatter the spin down electron, they do not scatter this much. Low scattering for spin up electron, high scattering for spin down electron. So, this is what both cobalt and gold does. Okay. So, here again we have color code. So, this dark green represents the scattering from cobalt. Okay. Cobalt scatters only the spin down electron. Okay. So, there is one scattering here from cobalt, there is another scattering here from cobalt. Okay. So, similarly, the gold is shown by this light green. So, gold also has alpha lower than 1. So, it will also scatter spin down electron. So, you can see this yellow spots shown by this green crosses. So, this is where the spin down electrons are scattered by gold atoms. So, in this system the spin up electrons flow freely, I mean less scattering for spin up electrons, whereas the spin down electron gets scattered a lot. Okay. So, in type 1 both types of electrons get scattered, in type 2 only spin down electrons get scattered. Okay, so, we use these results to understand the giant magnetoresistance under the current in plane scheme. Okay, so, we are, let us say this is one ferromagnetic layer, this is another ferromagnetic layer, and the blue is the spacer layer. So, in current in plane scheme we are sending current along this direction, right, electrons along this direction. Electrons are flowing this way. So, let us say electron current is flowing this, the conventional current is flowing this way, electrons are flowing this way. Okay, so, now remember everything that we learned. Okay, we have learned too many things. So, now as far as this ferromagnetic layer is concerned, let us say you have these two electrons. So, this electron is minority here. Okay. In this layer the magnetization is anti-parallel to this electron, this is minority. Okay. So, this electron will get scattered here at this interface of this particular magnetization. So, similarly, this particular electron, this electron is a majority here because these two magnetic moments are parallel. So, this electron is majority here, but when it goes to this electron is minority, okay, it gets scattered. Okay. So, when the magnetization are anti-parallel, whether you have one type of electron or another type of electron, they are minority in any of these two layers. Okay. So, both electrons will get scattered. Okay. So, this is like the type 1 alloy we learned. So, in type 1 alloy we learned that both spin up and spin down electron get scattered, right, which means the resistance of this path is high, resistance of this path also is high. So, when you have two parallel resistances where both resistances are high, your resistance of this particular parallel resistance is going to be high. Okay. So, that is what happens in GMR configuration where you have anti-parallel magnetization. Okay. So, you have two type of electron, this electron is majority here, but it is minority here. So, it will get scattered here, this electron will get scattered here again. Okay. Whereas, this blue electron will get scattered here because it is minority in this configuration. You see that this spin is like this magnetization is like this. Okay. They are anti-parallel. So, it is minority here. So, it gets scattered here and here. Okay. So, if you look at spin up channel and spin down channel, so you have large resistance in both of this path. Okay. Whereas, let us take the parallel magnetization. So, we have a GMR. Now, the two ferromagnetic layers have parallel magnetization. So, when it comes to this configuration, the red electron with magnetic moment in this direction is majority in both the channel. Okay. Red will not get scattered, but the blue electron which is in this direction, it is minority in both the channels. Okay. Because the magnetic moment of the two layers are pointing in the anti-parallel direction. So, the blue electron will scattered in both interfaces. Okay. So, in the second case, spin up electron have very low resistance, whereas the spin down electron has a very large resistance. Okay. So, it is because of this reason when the magnetization of the two ferromagnetic layers in GMR are parallel, you have the low resistance, and when the magnetization of the two layers are antiparallel, you have high resistance. Okay. So, if you are not very clear, again you will get the slides. So, you can go through the slides again slowly, and you can probably watch the YouTube recording also will be shared with you, you can watch again. So, it needs spending more time to understand what is happening here. Okay. So, I tried my best, but it will take more time for you to go through slowly and understand. The origin of anisotropic magnetoresistance I am not very clear, but they say that it is causing from spin mixing conductance and spin orbit coupling. But the simple picture that you can use for understanding AMR effect is that the S, D, the orbitals have certain orientation with respect to the current for magnetization parallel to and magnetization perpendicular to the current configuration. Okay. So, when the current and magnetization are parallel, you can see that the electronic orbits are perpendicular to the current. So, that means there is a larger cross section for scattering of S electrons. Okay. So, this gives rise to high resistivity when current and magnetization are parallel. Okay. On the other hand, in the perpendicular configuration, scattering cross section is lower when magnetization is perpendicular to the current. So, the resistance is lower. Okay. So, again if you do not understand this, okay, it takes a lot of time to understand this one. Let us use some simple analogy. Let us say there is a water pipe here, the pipe is there is a leakage, water is coming out. Okay, so, let us say I use this mouse pad like this, cover it, I can stop the flow, right. So, this one cross section. Let us say I do like this, okay, there is a water leakage here, but I keep my mouse pad like this, I cannot cover the flow, okay, the water flow will be there. So, in a similar sense, you can imagine that electrons are flowing this way, and when you have magnetization in this configuration, there is a larger cross section for scattering, you have more resistance, whereas in this configuration, okay, here is like this. So, the scattering probability is low, so the resistance is lower. So, here the cross section is like this. Okay, so, these are the theory behind AMR and GMR. So, let us now briefly look at the TMR sensor before we go for break. Okay, TMR stands for tunneling magnetoresistance. So, many of you would have studied tunneling in your quantum mechanics. Let us say we take a classical ball. Okay, so, this ball is at certain height. So, this ball is moving with certain velocity. So, we can say that the energy of this ball is half mv square plus mgh. Okay, so, that is the total energy of this ball, and when it rolls, it finds a certain height. Okay. So, if the half mv square plus mgh of the ball is more than the potential energy mgh1 of this barrier. So, we know that the ball will cross, right. So, energy of the ball is greater than the energy of the barrier, the ball will cross. Okay. On the other hand, let us say this is the ball and you have a very huge wall, okay, then the ball cannot cross, it will stop or bounce. Okay, so, this is what we know classically, but in quantum mechanics you know that electrons can behave like waves. Okay. So, we have a wave packet associated with electron. Okay, let us say in this case we have a barrier, and let us say we have an electron. So, this electron's energy in this case is lower than the barrier height. Okay. So, classically the electron is not supposed to cross the barrier, but quantum mechanically we know that the electrons have wave property. So, there is a wave function associated with the wave, and you would have studied in your quantum mechanics that when you have a barrier like this, this wave packet, it will decay exponentially here, and there is a probability that the wave continues here. Okay. So, when you have a thin energy barrier, for example, let us say this is alpha is the thickness of this energy barrier, the probability of this electron to tunnel So, I do not remember the formula, I think it is something like this. Okay. So, if alpha is small, there is a probability for the electron wave function to go to the other side. Okay. So, what it means that if you send electrons through a barrier, there is a probability that the electrons can go to the other side, okay, because of the wave nature and quantum mechanical probability of the electrons wave function going to the other side. So, how do we create this kind of energy barrier? So, for example, it can be like metal and insulator. Okay. So, if you take metal one side, insulator in the middle, then another metal on the other side, let us say you apply some electric field, then there is a probability for electron to go from this side to the other side. Okay. So, normally I mean when we have a wire like this, electricity flow we can touch without problem, because this whatever the black plastic or rubber is an insulator, right. So, in such applications the insulator is very thick, okay. Your insulator, this alpha is very large. So, the electrons do not tunnel from the current carrying wire to your body, okay, because the alpha is very thick. But if you make the alpha, the barrier, to be very thin, then there is a probability for electrons to tunnel. Okay. So, in this case we need to make this insulator very thin, that is important. So, if you make insulator of 1 nanometer or about 2 nanometer, then electrons can tunnel from this metal to the other metal. But if you make this insulator like 50 nanometer, then electron cannot tunnel, okay, because the tunneling probability is proportional to the, I mean it decays something like this. So, if alpha is large, then the tunneling probability will be very, very small. Okay. So, we can observe tunneling phenomenon when we use thin layers of insulator. So, we have two metals, metals have no problem in conducting electrons, but when you have thin layers of insulator, again like this. So, here we can say this is some insulator like magnesium oxide or aluminum oxide. So, electron can tunnel from one side to the other side. Okay. So, this concept is used in the tunneling magnetoresistance sensor. So, in tunneling magnetoresistance sensor, we have two ferromagnetic layers. So, if you look at this picture, the fonts are not very clear. One layer is called cobalt iron. This layer also is cobalt iron. Both are ferromagnetic layers. Sorry, no boron. Both are cobalt iron, and this layer that you see here is magnesium oxide. And this thickness is 5 nanometer. So, probably this magnesium oxide is around 3 nanometer or something. Okay. So, we just talked about simple tunneling. That means, if you have a metal and you have another metal, you have insulator, you send current, then there is a probability that electrons will tunnel and the current will flow. Okay. That is simple tunneling. Okay. When we talk about tunneling magnetoresistance, we are going to talk about spin dependent tunneling. Like spin dependent scattering we just saw in the GMR. In the case of tunneling magnetoresistance, the tunneling probability again depends on the spin of electrons and the configuration of the magnetic moments. Okay. So, again like in the GMR, if there are two magnetic materials, I mean if the magnetization of the two layers or antiparallel. So, here we have insulator. Okay, so, this is you can say this layer is cobalt iron, this layer is magnesium oxide, the third layer is again cobalt iron. So, if the magnetization of the two layers are antiparallel, you try to send electrons, the probability for electrons to tunnel from this side to the other side is lower. So, you will see the resistance is high, and if the two magnetization are parallel, then the probability for electrons to tunnel across is higher and the resistance will be lower. Okay. So, this is basically a simple explanation of tunneling magnetoresistance, and the significance of tunneling magnetoresistance comes into picture because of its larger values. So, we learnt that GMR is high compared to AMR. For most practical application, GMR is around 10% only. Okay. AMR is 2%, anisotropic magnetoresistance is typically 2%. Then when you have GMR, you can have around 10% change in the resistance. but with the tunneling magnetoresistance people have observed even larger values. Okay. In the industry itself they can make 200%, in the lab they have like observed 1000%. Okay. So, even compared to GMR, TMR was observed much earlier. Okay. It was observed in 1970s, but only at a low temperature. Okay. So, it was not useful for many years. However, in the middle of 1990s, these two scientists, Professor Jagadish Mudra from MIT and Professor Miyazaki from Tohoku University, Japan, again they observed almost at the same time that we can achieve TMR at room temperature. Okay. Since then people I mean in their discovery the TMR was around 16%. Since then people have improved this TMR to over 1000% in the lab and around 200% in the factory. So, people can really achieve this in factory. So, in factory you are making wafers like 30 millimeter, 30 millimeter diameter wafer, sorry 300 millimeter wafer. So, over large area you can deposit magnesium oxide films uniformly and you can demonstrate 200% TMR in factory, all due to sputtering. So, I told you that sputtering is the most reliable technology, right. So, over this large area you can make magnesium oxide 1 nanometer thick to achieve 200% TMR. Okay. PLD cannot achieve. Okay, so, now let us get back to what is TMR, what was the observation of TMR in 1996. So, in 1996 this group from MIT led by one Indian scientist Jagadish Mudra, he used 2 layers of ferromagnetic material. The one layer is cobalt iron, the second layer is cobalt, and he used aluminum oxide as the tunneling barrier, and he observed that at high field you know that the two magnetization will be parallel, resistance is low, and when you go towards lower field on the other side, one of the layer will change the magnetization. When the magnetization flipped and you see when they are antiparallel, the resistance is high, and again if you apply larger field they will become parallel, resistance becomes low. Okay. So, this is the path of this curve. So, similarly you go from this side to the other side, you will have this curve. Okay. So, they observe similar phenomena that we studied in GMR. So, in GMR also we have like when the magnetization are parallel we have low resistance, when the magnetization are anti-parallel we have high resistance. So, we see similar effect. So, in GMR we use 2 ferromagnetic layers and 1 spacer layer which is metal. In tunneling magnetoresistance again we have used 2 ferromagnetic layers, but use a spacer which is insulator. Okay, so, this is the key difference between GMR and TMR, and in GMR you can send the current this way or this way. Okay, in both cases current can flow. So, if you send current in plane, we learn that the electron will get scattered, they will go this way. If you send current this way, again they will get scattered, come like this. But in the case of TMR, the tunneling magnetoresistance, we cannot use current in plane. Okay. If you send current in plane, then because of this insulator, the electrons do not go into the other side easily. Okay. So, we cannot use current in plane, we can only use current perpendicular to the plane, because we are talking about sending a stream of electrons and looking at some electrons having the probability to tunnel to the other side. Okay. So, we use TMR only in the current perpendicular to the plane configuration. Okay, this one I already answered this question. So, we do not do this. Okay, for TMR, to understand the theory of TMR, there are two models. Okay. So, I told you that the TMR was observed in 1970s. So, there is a very old model called Julier model. Then there is also a recent model proposed by Butler. Okay, so, there are two models for the understanding of TMR. So, today I mean for the time being, let us look at the old model, Julier model. Okay, so, we have two ferromagnetic layers, either the magnetization are parallel or anti-parallel. We are sending electrons from this side. Okay. These two ferromagnetic layers are separated by insulator. Okay. So, when we talk about TMR, we usually use the conductance G. Okay. When the two magnetization are parallel, we have Gp. So, conductance in the parallel state. When they are anti-parallel, we have conductance in the anti-parallel state. Okay. The definition of TMR is the difference between the two conductance divided by the conductance in the anti-parallel state. So, here again we can use the idea that we studied in Mott's two current model. Okay, so, there is a separate path for spin up electron, there is a separate path for spin down electron. So, we have two channels for spin up and spin down electrons. Okay, so, now let us go into the details. So, according to Julier model, the tunneling probability or the conductance as a result of the tunneling probability depends on the density of states of the left. So, here we use ferromagnetic layer 1 or ferromagnetic layer 2, or we can use ferromagnetic material on the left side and ferromagnetic material on the right side. Okay. So, here this paper they use the symbol left and right. So, the probability for spin up electron to go from one side to the other side depends on the density of states for the majority electrons in the left side ferromagnetic material. So, we have two ferromagnetic material and the right side ferromagnetic material. Okay. So, we have various values of G for the different types of electrons. Okay. So, the G parallel, I mean when the two magnetic layers are parallel magnetization, we have this G, and when the two layers have anti-parallel magnetization, we have this formula. So, you can notice that all these G's are related only to the density of states. So, what all this means is that, let us say you have let us say this is the density of state of the left side ferromagnet, then we have another ferromagnet like this. Okay. So, this up going into this down going into this, and this up going into down, and this down going into up. So, all these tunneling probabilities are shown here. Okay. So, if you put all those things, okay, you do not need to know everything here. Simply it will turn out that the TMR depends on the difference between the number of up and down electrons in the shell and so on. Okay. So, this is one model. Okay. So, what it states is that in this case the probability of tunneling depends on the available states and so on, number of electrons that can go from one side to the other side, and the density of states available on the other side. Okay, we will learn the other theory later. Okay, so, in reality TMR sensor will look like this. So, we learnt that we want to fix the magnetization direction of one of the layers. So, to fix this magnetization direction in one layer, we have some antiferromagnetic material. So, we learned this before in GMR. So, we fix the magnetization direction of this layer with antiferromagnetic layer. So, instead of metallic spacer, now you have magnesium oxide as a spacer, then you have another ferromagnetic layer which is free layer. Okay. So, here again in the absence of a magnetic field, the two layers magnetization will be perpendicular. Okay. So, the free layer magnetization will be pointing along this direction, the fixed layer is in certain direction. Okay. Like this. So, if the magnetic field from the recording media is going up, it will force this magnetization to be parallel, and if the recording media magnetic field is pointing down, these two magnetization will be anti-parallel. Okay. So, it is very similar in concept, but we are using only the CPP geometry. Current is flowing in the perpendicular direction, and we are looking at the tunneling probability through the magnesium oxide. So, the tunneling probability is high when the magnetization are parallel, and the tunneling probability is low when the magnetization are anti-parallel. Okay, here I show some a little more complex design, which we will discuss another time. Okay, so, in this slide I have summarized the difference between GMR and TMR. So, GMR is basically ferromagnetic material, metallic spacer, ferromagnetic material. TMR is ferromagnetic material, insulating material, ferromagnetic material. And in GMR you can use both in plane, current perpendicular plane. TMR you can only use current perpendicular to the plane. GMR is usually very low value, around 10%. TMR theoretically 1000% is possible. In the lab people have demonstrated 500%. In the industry people can achieve 200% TMR. Okay, the resistance variation is large here, and the resistance itself is large in the case of TMR. Okay, because we are looking at current flowing through an insulator, right. So, the resistance of the TMR sensor is usually high. Okay, so if you look at the industry introduction, we learnt about AMR. AMR was introduced in 1990s. We learnt about GMR. GMR was introduced somewhere in 2000. Then TMR was introduced in the middle of 2000. Okay, so you will have all the slides. You can go through the slides again and watch all the videos to understand, because I mean, some of these concepts are very tough. The only difference in GMR and the TMR is the use of very thin layer to achieve electron transport via tunneling. That gives rise to significant increase in resistance change, and only CPP being possible in TMR. Yes, yeah, mostly right. Yeah, you are sending current. I mean, if you are talking about current in plane, you are sending current in one particular direction. I mean, conventionally electrons flow in the opposite direction to the conventional current, right. So, both spin up and spin down electrons are flowing in the same direction, but you can imagine that they are flowing in two different channels. Okay, I mean, one additional point to Moditma, what I wanted to say. So, in GMR is spin dependent scattering, in TMR it is spin dependent tunneling. Okay, that is the difference.
In the TMR section, you said that depend on the density of state, the electrons tunnel. So, if the density of state is more, the more tunneling or the less tunneling?
Okay, we'll discuss after break. Okay, now it's 11:30. We'll go for a break, then come back. Okay, so we are roughly halfway through the course. So I want to hear from you how it goes. So I prepared some questions through WooClap. So please answer them. I'll have a look at them later. Okay. So join using this link. Okay, so yeah.
Department has given this.
Okay.
So like you can fill and then give me later, so I have to submit
Okay.
in the office. Please
Okay.
get everything.
Yeah. Okay. Oh, okay. You mean this one? Okay. Yeah, you can use this. Okay, next one. Okay, so this is the last question. Okay, thank you all. So, today until the lunch time, I will cover two miscellaneous topics. Okay. One is on synthetic antiferromagnetism, because we will encounter this a few times in the later part. Then second concept that I will teach is thermal stability. Okay. So, these topics we will touch today. Then tomorrow onwards we will start learning about MRAM. How do we write information, how do we store information, how do we read information in MRAM. So, all those things we will start learning from tomorrow. Okay. So, the first concept we are going to learn today is synthetic antiferromagnetism. So, we learnt about ferro and ferrimagnetism. So, in ferromagnetism we learnt that the neighboring moments will be parallel to each other, and J is positive, and this is an ordered magnetic system. And in ferrimagnetic system we learnt that J is negative. So, the neighboring spins are antiparallel, but they are of different magnitudes. So, there is a net magnetization. Okay. So, this is something that we already learnt. We also learnt about antiferromagnetism, which is also ordered magnetic system. Neighboring spins are antiparallel, and their net magnetization is 0. Okay. So, we also have learnt about their use in exchange bias. So, we learnt about spin valve. So, in spin valve we want to keep the magnetization of one particular layer in one direction. So, we keep this ferromagnetic layer in proximity to antiferromagnetic material, and we follow certain recipe to achieve this exchange bias. Okay. All these things we have learnt. So, what we are going to learn today is synthetic antiferromagnetism. What is synthetic antiferromagnetism? Okay, so, when we say synthetic antiferromagnetism, I mean by the word itself, synthetic means it is not real antiferromagnetism, but we are somehow synthesizing a kind of antiferromagnetic system. Okay, so, in this system what we do is like we have two ferromagnetic layers Fm1 and Fm2 separated by some spacer layer like ruthenium, iridium, and so on. Even if you remember the GMR concept that we learned, so when we learnt GMR, we learnt that in iron, chromium, iron, the magnetization of the two layers at remnant were in the opposite direction. Okay, so that is a form of synthetic antiferromagnetism. Okay. So, when we are talking about synthetic antiferromagnetism, we are talking about two or more magnetization in anti-parallel direction. Okay. So, this is different from the antiferromagnetism. So, antiferromagnetism, I mean if you take a antiferromagnetic material, apply some field, let us say 1 Tesla field. So, with 1 Tesla field you will see that the magnetization is almost close to 0. Okay. With 1 Tesla field you cannot do anything, the magnetization of the neighboring atoms are still antiparallel, the neighboring magnetization is 0. Okay. Whereas, in the case of a synthetic antiferromagnetic material, let us say at resonance maybe the magnetization can be 0. Let us say if the magnetic moment of this layer and the magnetic moment of this layer are the same, magnetization will be 0 at resonance. Okay. But if you apply a high magnetic field, we can make both the layers pointing in the same direction. So, if you remember the GMR, we applied certain field like 2 Tesla, then we forced the two magnetization to be parallel. Okay. So, we can do that. So, in this case the magnetization can be very high. Okay. So, in synthetic antiferromagnetism, we are creating some form of antiferromagnetism by taking 2 or more ferromagnetic layers and separating by some spacer layer. So, because of this spacer layer, the neighboring layers are aligned in antiparallel direction. Okay. Okay, so it's a artificial arrangement. Okay, that's why we have the name synthetic. So, artificial arrangement of magnetization in antiparallel directions at resonance. Okay, so at 0 field. So, this kind of materials can be formed by depositing 2 ferromagnetic layers close to each other in the presence of a spacer layer that separates them. So, this spacer layer can be ruthenium, iridium and things like that. So, I mentioned that if the magnetic moment of these two layers are identical, then the net magnetization can be 0. But if say one layer is thick, another layer is thin, okay, and if they are arranged in antiparallel direction, we may have some net magnetization. Okay. So, is full or partial cancellation. Okay. So, when they are like almost equal thickness, the magnetization of one layer will be completely cancelled, you will have 0 magnetization, that is full cancellation. If one layer is thicker than the other layer, then the magnetic moment will be partially cancelled. Okay. So, for synthetic antiferromagnetism, we need at least 3 layers, So, you should have one ferromagnetic layer, one spacer, another ferromagnetic layer. So, let us say if you want to deposit a SAF structure, how many targets at least you need? At least 2, yeah. So, you can use the same ferromagnetic layer, for example, say iron, chromium, okay, something like that, or cobalt, ruthenium, something like that. So, you need at least 2 targets and at least 3 layers to make a synthetic antiferromagnetic structure. Okay, so, quite often people may get confused. So, here I summarize everything, compare everything. So, when you are talking about antiferromagnetism, you are talking about atomic magnetic moments being antiparallel. Whereas, when we talk about synthetic ferromagnetism, we are talking about magnetic moments of layers. Magnetic moments of ferromagnetic layers. Okay. So, when we talk about synthetic antiferromagnetism, we are talking about antiparallel alignment of two magnetic moments of one or two ferromagnetic layers. Okay. So, when they completely cancel each other, we can call them synthetic antiferromagnetism, and if they do not cancel each other, some people call it synthetic ferromagnetism, but loosely everyone calls both as a synthetic antiferromagnetism. Whether you cancel the net magnetic moment or do not cancel, people sometimes loosely call everything as synthetic antiferromagnetism. So, in antiferromagnetism, the interaction itself detects, interaction itself is like J is less than 0. In synthetic antiferromagnetism, we use certain layers that give rise to this kind of interaction. Okay, let me erase this one. Okay, so, in antiferromagnetic material, the interaction between two magnetic moment is determined by the exchange interaction, which is less than 0. But in synthetic antiferromagnetic material, we are using layers where J is greater than 0, because these are all ferromagnetic material, right. Okay, so, as I mentioned a few minutes ago, the origin of synthetic antiferromagnetism starts from the discovery of giant magnetoresistance. So, the discovery by Albert Furt's group, they found out that at 0 field, the two ion layers have antiparallel magnetization, but when they apply sufficiently large magnetic field, they can force them to be in the same direction. Okay. So, this is one of the earliest observations of synthetic antiferromagnetism. And similar results were also reported by Professor Peter Grunberg. Okay. They also observed similar behavior, but in system where they have only two ion layer. Okay, so, this we have already seen. So, after this study was reported, this scientist called Stuart Parkin, he did a very systematic study of inserting various spacer layers between two cobalt layers. Okay. So, if you look at this paper, you will see that he has used around 40 spacer layer, for example, around 40 layers. So, he studied the exchange interaction between the two cobalt layers separated by various spacer layer materials, and they observe this kind of oscillation in the resistance or saturation field. Okay. So, you can notice that when the ruthenium thickness is varied, the saturation field is oscillating. So, what it means is that for some thickness, for example, let us say this A, B and C, you will have anti-parallel alignment of magnetic moments between the two cobalt layers. However, if you look at points D and E, so in points D and E, the two ferromagnetic layers have same magnetization direction. Okay. What it means that the synthetic antiferromagnetism is observed only at certain thicknesses. So, thickness A, you observe this, the thickness value of B and C, you observe this, and D and E, you do not observe. Okay. So, depending on the thickness of this layer, only certain thickness you will observe the antiparallel coupling. Okay. So, that is the oscillatory behavior. So, some other thickness you may have like milder values of coupling. Okay. So, from this study through such study, okay, maybe let me explain what is this saturation field. So, at resonance, the two ferromagnetic layers are antiparallel. So, when you apply a very large field, the two layers will point parallel to each other. Okay. So, that field where the field at which the two layers have parallel magnetization is called a saturating field in this case. Okay. So, when the saturation field is very large, what it means is that the anti-parallel coupling between these two magnetization is very strong. Okay. So, when this coupling is very strong, we need very large magnetic field to overcome this coupling to produce the parallel state. Okay. So, that is the meaning of the y axis in this picture. Saturation field is large means the coupling is very strong. So, at this thickness the coupling is not that strong. A and B, the coupling values are not that strong, but when you go somewhere here, the coupling strength is very large. Okay. So, this is one observation then they made, and so I told you they studied like 40 different material, out of which they found ruthenium and iridium to have the high synthetic antiferromagnetic coupling. For example, let us say this is ruthenium, right. In case of ruthenium, they find something like this. If you do iridium, maybe it is even larger, something like this. Okay. I am roughly drawing to give you some perspective. Iridium has been reported to have very large exchange coupling compared to ruthenium, and compared to this other materials are much inferior, like let us say you take copper for example. In the case of copper, maybe this coupling is like very weak. Okay. So, after this study, people have used ruthenium as one of the main layers to introduce this synthetic antiferromagnetic coupling, but in the recent past, the MRAM companies, the companies that make MRAM, they also start using iridium, because iridium gives even large exchange coupling. So, this SAF is very useful. Okay. It is not just a physical observation which is useless, but it has lots of use. Okay. So, I will show you a few uses of this synthetic antiferromagnetism. Let us say we go back to our spin valves. So, in spin valve we learnt that we have an antiferromagnetic layer, we have a ferromagnetic layer which is pinned in one particular direction, then we have a spacer layer, then we have a free layer. Okay, so, whenever I draw an arrow, you can imagine that this is like a magnet, right. So, you are magnetizing a material in one particular direction. So, this is like a tiny magnet. So, you know that magnets will generate a magnetic field. Okay, so, this layer will generate some magnetic field. So, this magnetic field will influence the magnetization direction of the free layer. Okay. So, for example, this is north pole. So, preferably having south pole here is more favorable, okay, because you know, like when you have two magnets, if north south and south north are like in contact, that is more stable, right. So, if you magnetize this layer in one direction, this magnetization, I mean north south, this is favored, whereas the other direction is not favored. Okay, so, if you have only one reference layer or fixed layer or pinned layer, if you have only one pinned layer, it generates a stray magnetic field, and that stray magnetic field only one favors one particular magnetization direction than the other direction. Okay. So, this is the problem. So, people try to overcome this problem by splitting this one layer into a synthetic antiferromagnetic layer like this. Okay. So, instead of one ferromagnetic layer like what we studied before, now we have two ferromagnetic layers separated by ruthenium. Okay. So, because of the ruthenium, these two layers will have antiparallel magnetization. So, now if you look at the stray field from this particular layer will go here, and the stray field generated by this layer will go here, and none of this stray field will go to the free layer. Okay. So, now free layer is not affected by the stray field of the pinned layer. Okay. So, whether in MRAM or spin wall, the reference layer or the pinned layer is now always based on synthetic antiferromagnetism, because we do not want any stray magnetic field to come from this layer. Okay, so, this is one real life use of synthetic antiferromagnetism. The second use is in recording medium. So, in some earlier form of recording medium, longitudinal magnetic recording. So, people used this instead of one recording layer, they used recording layers, two recording layers with a separated by ruthenium. So, they have antiparallel coupling. Because of that, there is some use which we do not go into detail. Then another use also is in perpendicular recording medium, where they again they divide a ferromagnetic layer into a soft magnetic underlayer, and that helps in reducing the noise from the recording medium. Okay. Okay, you do not need to go through this detail, because we are not studying recording medium, but you can just simply appreciate that synthetic antiferromagnetism is also used in recording medium to reduce the noise from the recording medium. Okay. This is another application. So, similarly, when we learn MRAM, I will introduce that we are also using synthetic antiferromagnetic structures in MRAM. So, today I will not go through this, but when we learn MRAM, we will go through this. Okay. But just remember that synthetic antiferromagnetism means we have two ferromagnetic layers separated by ruthenium, which induces antiferromagnetic antiparallel alignment of magnetization. Okay. So, just remember this when we learn about MRAM.
Sir,
Yeah.
how does this layer ruthenium or iridium is facilitating antiferromagnetic coupling between the two layers? I mean, what is the mechanism?
How does it introduce? Okay. I mean, long ago, there was a theory called RKKY. So, this theory is from 4 scientists, Ruderman, Kittel, Kasuya, something like that. There are 4 scientists. They came up with a proposal that let us say you have some spins when they are mediated by some non-magnetic material. So, okay, here there is no arrow. Through some non-magnetic layer, they can still have some interaction, and depending on this non-magnetic layers material and the spacing between them, you can have oscillatory coupling. So, these two spins can have parallel coupling or anti-parallel coupling. So, which will be something like this, which you saw in some few slides ago. Okay. So, there is this model called RKKY to explain why this is happening. Okay. So, if you want to know more, you can Google RKKY and understand this model.
So this double exchange interaction or something is a part of this RKKY?
Double exchange interaction is different, right? You are talking about
in the SAF,
Mhm.
the two ferromagnets are like in the antiferromagnetic coupling.
Mhm.
So they are communicating by some mechanism in between because of the spacer layer.
Mhm.
So what the mechanism, like RKKY is happening, so is that double or the super exchange interaction something happening?
No, it is not double or super exchange. I think you read about RKKY, then you will understand. Okay. Okay, so if you have only one ferromagnetic layer, we know that the hysteresis loop will be symmetric with respect to the center of the MH loop. But when you have two ferromagnetic layers separated by ruthenium, for example, let us say this is their ground state. Okay, in the absence of field, let us say this is how they are supposed to look like. If you measure the hysteresis loop of such a sample, it may look like this. Okay. So, at very high field, the magnetization of the two layers are parallel. When you come closer to 0, the exchange coupling between the two layers makes this one of this layer to flip. So, you will see that the magnetization drops here. So, this is the region at which this magnetization flips from pointing up to down. Okay. Then when you go further, then both layers again point in the same direction. Okay. Then again you go from this side to the other side. This is retained in the same direction, but this layer, the blue layer, flips. Then when you go further, both layer flips in the same direction. Okay. So, typical SAF samples will have some behavior like this. At least one magnetization will reverse before the 0 field. Okay, so you can measure the strength of exchange interaction by measuring a minor loop. Okay. When I say minor loop, what I mean is like you start from here, for example, you go all the way, this layer has flipped, let's say you stop at this point, then go back, then you will see something happening like this. Okay, so this loop is called minor loop. Okay, so here you see the minor loop, real minor loop. So the center of this minor loop has shifted from 0 field by a certain magnetic field, and this is what we call as exchange field. Okay, so this exchange field is related to J. J is the coupling introduced by this spacer layer. So, for example, if you have ruthenium, ruthenium introduces certain J that forces the two magnetization to be antiparallel to each other. So, this is the J, and MS is the magnetization of this particular layer that switches, and T is the thickness of that particular layer that switches first. Okay. So, if you know the MS of this material and its thickness, and you measure HEx by doing minor loop, you can calculate the interaction strength. Okay. So, this is how we calculate how much the exchange interaction produced by spacers like ruthenium or iridium. Yes.
Minor loop in the sense that it has it's leading only, or sometimes if the loop is not closed, we say sometimes.
Yeah. So, basically if you go from saturation, a very large field that saturate all the layer to another side saturation, then come back to saturation again, that is a major loop. Okay. But if you do not do that, then that is a minor loop. Okay. Let me give you some example. For example, you have a piece of magnetic material. If you apply very large magnetic field, you will have some hysteresis loop like this. Okay. Let us say this is 7 Tesla. Okay. But in my lab, let us say I have a magnet with only 2 Tesla magnetic field. Okay. So, if I measure this same sample using 2 Tesla magnetic field, so I may go from here to here, then I cannot go beyond 2 Tesla, then I will come back and I will see something like this. Okay. You see that it is not saturated. So, only when you apply 7 Tesla, this loop will get saturated, but here I am applying much smaller field, which is not enough to saturate. So, I get some, still I get some loop. So, this is called a minor loop. So, in this case again we are going from saturation, but we are stopping somewhere here, right. We are not going all the way to the other side. So, this is called a minor loop. Okay. So, that is about synthetic antiferromagnetism. So, someone asked me during the GMR why with chromium, different chromium layer thickness. So, if you remember the GMR curves, they are saturating at different fields, right. So, for chromium 18, the saturation happens somewhere here, chromium 12, the saturation happens somewhere here, chromium 9, the saturation happens here. That is because with respect to the chromium thickness, you may have some oscillatory coupling. So, maybe some of them are here, some of them here, something like that. So, depending on the thickness, you will have larger or smaller exchange coupling. So, maybe 9 is here, 9, 12, let us say this is 9 angstrom chromium, 12 angstrom chromium is here, then 18 angstrom chromium is here, something like that. So, in this particular set of samples, luckily they are all these samples are in the same with a positive negative J, which can introduce antiparallel magnetization configuration. Okay, so with that let us move on to the second topic.
One is before breaks from fusion. In GMR device, if thickness of ferromagnetic layer is more than the mean free path of the electron, how does this affect?
Then you, I mean, first question, Pooja Narvat, if the thickness of the ferromagnetic layer is more than the mean free path of electrons, maybe your GMR will be reduced. So, the GMR effect will be reduced as you keep increasing the ferromagnetic layer thickness more and more. So, beyond certain value you may not be able to observe GMR.
Other question is after what properties should have a materials to use as a special layer?
Yeah, this one is difficult to say, but as I mentioned in 1990s itself, Professor Stuart Parkin, he has studied 40 different materials. So, from which ruthenium and iridium are known to be a good material. So, why you want something else? Just use one of them, ruthenium or iridium. Okay, so the next concept that I am going to introduce is thermal stability. So, this is completely in contrast with what we learnt early in the morning. Early in the morning you learnt very hard theories. Now, we are just going to listen to some story, okay, because it is lunch time. I do not want to teach you hard subject. Okay, so, I am going to introduce you to the concept of thermal stability by showing the progress of magnetic recording technology, because as I told you many times before, magnetic recording technology is the parent home from which everything for MRAM came about. So, when we learn about thermal stability of MRAM, again the concepts come from recording technology. Okay, so, we learnt all these things. Some of these things I skipped. Okay, so, when you want to make recording media better and better for high densities, basically what we do is we make the grains that store the information smaller and smaller. So, you see the diameter is getting reduced, the height is getting reduced and so on. Okay, so, let us start from here. So, the hard disk technology was introduced in 1956. At that time the hard disk looked like this whole piece, which people use some heavy equipment to move the hard disk drive, or the hard disk drive that could store 5 megabyte. Okay. But now we can easily have hard disk drives with 5 terabyte capacity. Okay. You can put them in your pocket. So, from this size we have come to this size, and from 5 megabyte we have come to a capacity of 5 terabyte, which is 1 million times larger. Okay. So, this is the growth that has happened in the hard disk drive. So, I always tell how much we have miniaturized everything by using this example. Okay. This example I created in 2000s, but at that time this was the tallest building in the world. Okay. So, this is called Petronas Tower in Malaysia. So, when you compare the bit length of a hard disk drive in 1956 to the bit length of a hard disk drive now, the scaling, I mean the reduction in the bit length is like shrinking this whole tower to this size. Okay. Imagine the miniaturization of a tower as tall as Petronas Tower to this small size. Okay. So, that much miniaturization has happened in the bit length. Okay. So, similarly you take the width of the track. width of the track, let us say it was as wide as this Petronas tower in the first hard disk drive. Now, it is this size 1 inch. Okay, so, this much miniaturization has happened. Because of that, now we have like very high density hard disk drives, because we can pack more bits. So, the price that we pay for every gigabyte was falling down and so on. So, this kind of growth happens in two ways. One is called scaling, another one is called major technological jumps. Okay. So, when we say scaling, what do we mean is like, let us say these are the bits of say technology in 1980s. So, the bits are this length and this wide. Then let us say we create another technology in 1985, we have made the bits smaller in length and width. As we move further, we make the bits even smaller and less wider. Okay. So, this kind of progress is called scaling. So, you reduce the bit length, you reduce the track width by certain percentage, then we call it scaling. Okay. So, scaling looks simple, but it is not easy. Okay. So, to achieve this, you need to make the grains smaller by certain size, you need to increase the coercivity, the material property you have to improve and so on. So, you do so many things, then you can scale the bits smaller and smaller. So, to give you some perspective, this is some very old technology where the bit length was 200 nanometer, this one is 200 nanometer and this width is 2.5 micrometer, and you can measure this kind of bits using MFM. Okay. So, this was possible before 2000. So, mid of 1990s you can measure the bits using MFM, but in current technology this length is only 10 nanometer and the track width is only 40 nanometer. Okay. So, 10 nanometer is even beyond the resolution of MFM. You cannot use MFM to visualize the bits like you did in the past. Okay. So, this is the kind of growth that is happening. So, that growth happens by reducing the grains smaller. Okay. So, let us say in technology, one particular technology your grains are this big, when you move to another technology where the bits are small, you make the grains smaller, even smaller. Okay. The diameter of the grains getting reduced. So, this is one real life example. So, suppose I look at the grains of this technology. So, you store 7 gigabit in a square inch. In this technology you can see the grains are bigger, but if you go to another better technology, you can see the grains are smaller, very well separated and so on. Okay. So, if you look at the history of grain size, so this is the increasing areal density. As you pack more and more bits, you can notice that the grain diameter keeps reducing. Okay. We are reducing the diameter of the grains as much as possible as technology grows. So, in recent hard disk drives, you can find 15 trillion grains in a square inch. Okay. So, in 1 square inch, which is this small, okay, within this area you will find 15 trillion tiny grains in a square inch. So, that is the progress that we have, that is one thing. Secondly, I told you briefly about pulse width, this also we need to reduce. So, to reduce pulse width, we need to reduce the MR multiplied by thickness. So, in this picture you can see that this MRT has been reduced. So, this is typically reduced by reducing the thickness. Okay. and coercivity has to be increased. So, all these things happen. Okay. So, basically scaling means reducing or increasing certain parameters. So, reduce MRT, increase coercivity, reduce grain diameter. So, all these things have been happening in the hard disk industry. So, what is the implication of this? Let us skip this. So, there is some implication. Okay. So, what is the implication? I will tell you after telling this story. Okay. So, we all claim that chess was invented in India, right, but Russians claim that chess was invented in Russia. So, this story happens in Russia, okay, because this is written by someone else. Okay. So, in this case the person who invented chess, he goes to the king and describe him the game of chess. The king was very happy. Okay. So, the king asked, what do you want? Then the person who claimed to have invented chess, he tells the king that I want 1 wheat grain for the first square, then 2 for the second square, 4 for the third square, 8 for the fourth square, and things like that. So, it is going in 2 power 0, 1, 2 like that. Okay, then the king thought this is very simple. Then he ordered his people to go and offer this price. Okay. So, a few months later the people come and complain to the king that we do not have any more stock of wheat grains to give it to the inventor of chess. Okay. So, that is because of the way exponential power or 2 power something happens. Okay. So, if you go to the 64th square, right, you will need like 2 power 2 times 10 power 19 grains, which is like 1.2 times 10 power 15 kilogram, which is actually more than the worldwide production of wheat. Okay. So, obviously that kingdom cannot deliver their promise. Okay. So, the moral of the story is, like anything, any technology or whatsoever, if you go from the first board, I mean first square to say somewhere in the middle, you can climb, but after that you will get, it will get tougher to climb. Okay. So, it happened in semiconductor technology. So, Moore's law enabled doubling of transistors, but now we have reached a place where it is difficult to go from say even the 32nd square to 33rd square. Okay. So, that is tougher. So, in the similar sense, hard disk industry also has grown from say like 5 megabyte to around 5 terabyte now, but now we have lots of challenges. Okay. So, to go from 5 terabyte to 6 terabyte itself will be very, very challenging. Okay. So, that is because we have been like shrinking the diameter of the grains. So, from like 50 nanometer we have come down to around 8 nanometer, or we can shrink from 8 to 7 or 7 to 5. That is very challenging, that is one thing. So, we have been shrinking the diameter of the grains and we have been reducing the thickness of the grains. So, you can notice that in a low density hard disk drives, these grains which store the magnetization have a larger volume, and here you can notice that the grains have a smaller volume. So, we learnt that the energy barrier that keeps the information stable is proportional to KUV. Okay. So, you can notice that the KUV, I mean if you keep the KU same, for example, you use the same material for example, then the volume has gone down, which means KUV has reduced a lot as we progress towards certain direction. Okay. So, that results into a problem called thermal stability of magnetization. Okay. So, in this case I mean this is a cartoon image, not a simulation. Okay. So, I am just using some kind of cartoonist illustration of what happens to the magnetization. Okay. I apply a magnetic field along this direction and saturate the magnetization of these materials along this direction. Okay. So, let us say this is the cobalt cube. So, in this case is a 13 nanometer cube, 10 nanometer cube and so on. Okay. After I saturate, I remove the magnetic field. Okay. I observe the magnetization at 0 field. So, you can notice that the 30 nanometer cube retains the magnetization in the same direction, 10 nanometer no problem, but if you look at the 8 nanometer one, it flips very rapidly, and 8.5 nanometer also flips, but not that rapid. So, sometime it is pointing towards left and after some time it will point towards the right. Okay. So, this is called the thermal stability of magnetization, because this flipping of magnetization happens based on the competition between KUV and KBT. So, at room temperature we have thermal energy. So, this thermal energy competes with the anisotropy energy. So, as a result, when the volume becomes lower and lower, this becomes smaller. So, this energy can compete and make the magnetization flip as a function of time. Okay. So, when this flip is very rapid, then we call that a super paramagnetic. So, a few days ago we learnt about this. Okay. So, this is one example, real life example of something I measured myself. Okay. So, in this case I take a piece of sample, I put it in the VSM, I magnetize in certain direction. Okay. Then I remove the magnetic field and I observe the magnetic moment of the sample as a function of time. Okay. Field is 0. So, you notice that the magnetic moment keeps decreasing as a function of time. Okay, this is a logarithmic scale. So, it keeps decreasing as a function of time. Okay, so, this decrease of magnetic moment is because of the competition between anisotropy energy and thermal energy. Okay. So, this was explained by Neil many years ago. So, it is called Neil Arrhenius decay, where if M0 is the magnetization at a time t is equal to 0. So, this magnetization will decrease as a function of time. So, at time t, the magnetization T of that magnetization M of that material will be given by this formula, okay, where tau is the given by this one. Okay, so, we can see the anisotropy energy coming here, thermal energy coming here. So, this ratio, if this ratio is large, for example. So, if this ratio is large, this number is going to be large. So, if tau is large, this number is going to be small, then magnetization will not decrease much. Okay. On the other hand, if tau is small, I mean if KUV by KBT is small, KUV by KBT is small, tau will be small. If tau is small, this whole thing is going to be large, then exponential minus some large number means magnetization will decay drastically. So, that is what you see here in the previous image. So, this is a logarithmic, I mean kind of, it is not a linear scale, right. So, you see that the magnetization decreases because in this case KUV by KBT is small.
So here it's only based on the time, right? The axis, the magnetization is only a function with respect to time, right?
Magnetization is observed as a function of time.
Time.
Yeah.
The spin is trying to relax only.
Yeah. Okay, so in that particular sample, the KUV by KBT was small. So, tau is small and we see M decaying as a function of time. Okay, so this is the concept that leads to superparamagnetism, which we already discussed before. For example, if we have a collection of ferromagnetic particles and if they have very large KUV by KBT, then there is no time dependent magnetization decay. So, all the magnets, suppose you magnetize them north, up, south, down, something like this, they retain their polarity. So, even if you observe them after 1 year, they will be still pointing in the same direction. Okay. On the other hand, you look at these particles, they are small. So, their volume is small. So, KUV by KBT of these particles are going to be small, and temperature influences the magnetization. Okay. So, some of them have retained, I mean we cannot say retained, some of them point in the direction, but you can notice that several of the other grains have flipped the magnetization. At another point of time, you can see that they have flipped. Okay. So, as a function of time, the magnetization of these particles will keep flipping as a function of time, especially when KUV by KBT is low. Okay, so, that is why I mentioned that the red curve here, the red curve that you see here is the curve of a superparamagnetic system, and the black is the hysteresis loop of a normal ferromagnetic material with a large KUV by KBT. Okay, so, when we talk about paramagnetism, so we are talking about a competition between KBT and the magnetic moments. Okay. In the case of superparamagnetism, it is the competition between KUV and KBT. Superparamagnetism? Yeah, you might, okay, let us say you have certain piece of sample. So, at room temperature, you have this hysteresis loop, okay, superparamagnetic. But if you go to low temperature, let us say 4 Kelvin, the same sample may show some hysteresis loop, okay, because you are reducing the temperature, right. So, KUV by KBT. So, if you are reducing the temperature, denominator is lower. So, KUV by KBT will be larger. Okay, let us say at a T is equal to 300 Kelvin, KUV by KBT is 15, let us say. Okay, if you make this temperature to be 3 Kelvin, you notice that this gets larger, right. So, at a very low temperature, the superparamagnetic particles will open up, the hysteresis loop will be there. So, room temperature no hysteresis loop, but at low temperature you will see some hysteresis loop. Okay, so, here I roughly calculated the KUV, I mean for different KUV by KBT, how much of the magnetization will flip. Okay. So, if I wait for 100 seconds in samples up to keV by kBt of 50, there will be no change in the magnetization, but if keV by kBt is smaller, then you see the magnetization is dropping. Okay. So, it is like 1% drop, 9% drop. When it goes to 20, almost no magnetization. Basically, here we have super paramagnetism. So, when we design hard disk drive or MRAM, the industry is selling these products to a customer, right. Suppose I sell you some hard disk drive, say you store your thesis in your hard disk drive, and if the thermal stability of the hard disk drive is only 40, then maybe next day you try to open your file will be gone. Okay. But so, we cannot sell a hard disk drive with the keV by kBt is low. So, when people sell hard disk drive or MRAM, they will ensure that your data is stable at least for 10 years. Okay. So, if you store your data, if you do not touch, I mean you do not do anything, the data will be there for about 10 years. Okay. So, this is the aim. So, if you look at this picture, so when the keV by kBt is around 60, even after 10 years there is no change in the magnetization. Okay. Below 60, you will notice that after 10 years there is a drop in the magnetization, which is not desirable. Okay. So, usually hard disk drive makers ensure that your keV by kBt is at least 60, so that your data is stable for 10 years. So, the implications of thermal stability is like as I said before, if your keV by kBt is low, some magnetization will flip and you will lose your data. And in the case of hard disk drive, we are using polycrystalline material. So, some grains may be big, some may be small. Okay, there will be a distribution in the grain, right. So, the smaller grains will always flip and you will lose the data. Okay. So, because of all these reasons, people try to achieve keV by kBt of 60 or more. Okay, so, this is the cartoonist video of what happens when you go towards high technology in hard disk drive. If you are going towards higher technology, okay, you make the grain thickness smaller, diameter smaller. As a result, this magnetization is not maintained. You can see some grains are flipping. So, if you make them smaller and smaller, more grains flip their magnetization because of the competition between thermal energy and anisotropy energy. So, there is a limit to make the grain diameter or the thickness too small. Okay, I think we can stop here. So, whatever I wanted to teach you today, I finished. So, we have learnt about SAF and thermal stability. Okay. So, from tomorrow we will learn about MRAM, how do we write information, how do we read, what are the challenges in storing information in MRAM and so on. So, for the question of Moditma, yes, the sample was initially magnetized and magnetic field was removed and the magnetization was measured over time. Yes. Okay, thank you. We go for break, lunch. map also.
Can I ask a question now? If that is possible.
Yeah, okay, sure.
Can I ask a question?
Yeah, please go ahead.
Yes, sir, actually, this doubt about why we call it as scattering is when they say the electrons are occupying the vacant states, why we call it as scattering? Uh, scattering while
Your audio is very unclear. Can you type your question? Please type your question in the meeting chat, then we can discuss. So in spin dependent scattering, why we are referring to the phenomena as scattering of electrons. Okay, we are talking about resistance of material. When we are talking about magnetoresistance, we are talking about resistance of the material, and mostly in GMR, TMR, we are talking about metallic ferromagnetic system. So the electrons are the one that flow, which determine the resistance of the metals that we are talking about. So if you are talking about flow of electrons, then the scattering of electrons is supposed to give rise to the resistance, right? So we are talking about the scattering of electrons based on their spin. So up electrons, spin down electrons, they get scattered in different proportion. So that's why we say spin dependent scattering. So it's not ionic conducting material, right? So we are talking about conduction of electrons. So occupy d states, why it's called scattering? Because d state is localized. So in the atoms, s electrons are, I mean in metallic system, s electrons flow around, gives rise to the conduction, and d states are localized, right? So if electrons get scattered into d state, then they are not flowing, right? So going into d states is called scattering. Yeah, thank you.
When we discuss about this ferromagnetism, material